Scotty, can you start? All right, well, welcome back, everyone. We're happy to have Jenny Wilson from the University of Michigan, who will tell us about the high degree cohomology of special linear groups.
Wonderful. Thank you so much for the invitation to speak. It's a pleasure to be here. Um, so I was hoping to give a bit of a broader survey talk on one of the programs that I've been interested in for a few years, which is related to, I guess, in particular, the high degree cohomology of special linear groups. Um, and I will mention a few different pieces of work, some of which I'm involved with in the talk. And among the work I'm involved with, it will be joint with various subsets of Benjamin Brück, Alexander Kupers, Jeremy Miller, Peter Patzt, Robin Sroka, and Don Yasaki. Um, great. So throughout the talk, I will use the letter R to mean a number ring. So I mean the ring of integers in a number field, which is a finite field extension of the rational numbers. Examples of number rings to keep in mind are, say, the integers, the Gaussian integers, the integers adjoin your favorite root of unity, and so forth. And great. And so this program, broadly speaking, is interested in studying the cohomology of the special linear group with entries in this number ring. And I guess most significantly in the case when the number ring R is just the integers. So let me say a little something about what we know about these cohomology groups already. And I wish I could move this panel. I'm not sure if I can do that. I guess I'll scroll the screen. Sorry. Maybe I can zoom a little bit. Sorry. Okay. Thank you. So great. So what's known? Okay. So on one hand, it is a result of Borel. Let me write here. It is a result of Borel that if we consider, whoops, that's what I meant to do. Sorry. If we consider the inclusions of SLNR into, sorry, uh, SLN plus 1R that I get from, say, upper triangular embedding, then this inclusion map induces isomorphisms on cohomology in a stable range. So if we fix a degree Q and look at the induced map on cohomology, oh, in fact, this holds with integer coefficients even, then these induced maps will be isomorphisms once n is sufficiently large relative to Q in some, in this case, a linear stable range. So in terms of this table, what this means is that there's some range that is linear, beneath which we have stability. So along these horizontal lines, these groups stabilize. And the stable groups are known. So we can say that when Q is small relative to N, we have a pretty good understanding of what's going on. On the other hand, due to work of Borel and Serre, there is a known virtual cohomological dimension for these groups, which is known explicitly. It depends on specifically what R is. Somehow it depends on the Galois theory of the number field associated to R. But importantly, it is quadratic in N, and For whatever the definition of VCD is, for formal reasons, it means that our cohomology is going to vanish in degrees above the VCD. So we always have 0 above this range. And this is due to Borel and Serre. Okay. Great. So again, we have a reasonable understanding of what's happening here in low degrees. And the project I'm interested in is concerned with the question of what's happening up in high degrees. What can we say about the cohomology in degrees when Q is close to that virtual cohomological dimension? Okay. And also a slightly subtle point. So for formal reasons, we know the cohomology with rational coefficients has to vanish above the VCD if Q is higher than the VCD. But when Q is equal to the VCD, if I take trivial coefficients, it may or may not be 0. So somehow the definition of VCD guarantees for me that if there's some system of possibly twisted coefficients I could choose, where I would have non-zero cohomology in the VCD. But for specifically the case of trivial rational coefficients, we may or may not have vanishing. And so, in fact, even in the case of the integers, it is an open question, like what is the highest degree where you have non-zero rational cohomology with trivial rational coefficients? Okay, so an open question is what is the largest degree Q such that we have non-vanishing cohomology with trivial rational coefficients. This is in general an open question, at least for high values of n. Okay, and right, this is a question I will not answer in this talk. I do not know the answer to this question. But related to this question, there's a conjecture due to Church, Farb, and Putman that there is vanishing of these cohomology groups in a stable range close to the virtual cohomological dimension. So specifically, they said that if we look I degrees below the VCD, then these groups are going to be 0 once n is at least I plus 2. And these groups, this is a group they called the codimension I cohomology. Okay, so looking back at this chart that we were drawing, what this is saying is that conjecturally, there's this range close to the VCD where we have vanishing of the cohomology. And the specific statement says that the height of this vanishing range is growing linearly with n. Okay, compared to the quadratic growth of the VCD. And so Church, Farb, and Putman, they framed this conjecture as a sort of stability conjecture. They framed it as something that's in a sense dual to the classical Borel results about cohomological stability in low degree. And in fact, they gave 2 definitions of what could be a stabilization map that would induce this stability. So, which is a little bit surprising because in this case, this stabilization map is going to have to be something that jumps cohomological degree. So it's, in that sense, it doesn't fit into the classical framework of these sort of cohomological stability results. But they defined such a map, and they proved that if you do have stability with respect to this map, then necessarily the stable groups would have to be zero. And so they framed this, their description of it was that this is stability in the unstable cohomology, and in fact would have to be a sort of a vanishing result for cohomology close to the VCD. Okay. And in terms of, so I'm interested in this conjecture. I think it's a fairly fundamental question is, what can we say about the high degree cohomology with rational coefficients of the special linear group? And maybe a natural way to generalize the question, because as I'll talk about in a few minutes, the sort of context for the conjecture is very similar, would be to ask what happens if we replace Z in the conjecture, so replace our coefficient Z with another number ring. Okay, and you can ask in that case too, what happens when, what happens to the cohomology close to that virtual cohomological dimension? And in what way does this depend on the number ring? What properties of the number ring are relevant? Okay. And so here is the progress to date on this conjecture, or at least some of the progress to date on this conjecture. In the case of codimension 0, so when we consider what happens when Q is actually equal to the VCD, and when n is at least 2, this is what's known. Under the assumption that R is a Euclidean ring, so notably this holds for the integers, then it's a result of Lee and Sharba from the 70s that the codimension 0 the case of the conjecture does in fact hold. So we do have vanishing in the VCD of the cohomology of SLNR. And something interesting is that Church, Farb, and Putman proved that if, in contrast, if we look down here, if R is not a PID, then what they showed was that there is non-vanishing of the cohomology in the VCD. And in fact, they put a lower bound on the rational dimension of these groups in terms of the class number of R. So I think that's interesting. It's interesting that these ring theoretic properties of R are really showing up in these cohomology groups. Okay, so this leaves the open case of rings that are PIDs but are not Euclidean. And in fact, it's a theorem of Weinberger that apparently, if you assume the generalized Riemann hypothesis, then the only number rings that fall into this category, the only number rings that are PIDs but non-Euclidean, have to be quadratic number rings and specifically, they have to be one of these 4 quadratic number rings. So this is not a theorem. This is a theorem. It's true if you believe the generalized Riemann hypothesis, then we have a short list of all such rings. Okay. And in work with Miller, Patzt, and Yasaki, we showed that in that case, we also have non-vanishing of these cohomology groups in even degrees of n. But the result is open, I guess, when in the case n is odd. And it's also open completely open in the case when d is 19. So if you consider the ring of integers uh, in the quadratic um, number field given by attaching adjoining the square root of -19, then it's open. Okay. So again, interesting that it seems to depend on these ring theoretic properties of R. Let me move this over. Okay, so the next case is the case of codimension 1. What happens 1 degree below the VCD? And their results of Bykovsky and Church and Putman prove the conjecture for the integers in that case. So in that case, you do get vanishing of the cohomology if you go 1 degree below the VCD. And with Cooper, Miller, and Patzt, together we adapted the methods in this work of Church and Putman to study these other two examples of Euclidean rings. So to study the Gaussian integers and the Eisenstein integers. And we found that we also have vanishing in this case. But something that was surprising to me was that this approach ended up using actually fairly specific geometric properties of the lattices you get associated to these two number rings. And unlike this, these earlier results by, say, Lee Sharba, where it's really clear that the key feature that you're using in the proof is the Euclidean property of these rings, the proof over here was using definitely more than just the fact that it was Euclidean. And in fact, the proof provably fails for some Euclidean rings. So I think that is to say, we really don't understand very well what's happening in the case of this codimension 1 conjecture. And again, it seems to use some sort of surprising, I mean, this particular proof seems to use some fairly surprising properties or some properties I don't know how to think about really of these rings in a way that I don't understand very well. So I think that's interesting. Finally, the last case that we have an answer is the case of codimension 2. In the case that R equals Z, in that case, in joint work with Brück, Miller, Patzt, and Sroka, we proved again that the Church-Farb Putman conjecture for vanishing does in fact hold in codimension 2. And the approach we took to this proof, in principle, maybe could be generalized to higher codimension, except that on one hand, it was using some properties of the Voronoi, of like the Voronoi tessellations that it's unclear whether they will generalize appropriately. And on the other hand, our proof, as written, ended up using some computer computations to prove that some short list of a few hundred simplicial subcomplexes were contractible. And it's also unclear whether that step in the proof is scalable. So I think suffice to say, with current methods, we do not know how to go beyond codimension 2. Okay. Okay, so
Sorry.
yeah,
Can I ask
please.
a question before you go on? In the
Yeah,
codimension 0 case,
yeah.
is there anything quick you can say about why D equals 19 is exceptional?
Oh, yeah, sure. Well, I mean, I mean, I don't know if this is a satisfying answer or not, but the way our proof worked, roughly speaking, was that we managed to somehow bootstrap known computations in the case that n equals 2 and somehow like propagate like known non-vanishing groups through a spectral sequence argument in order to produce non-zero classes in higher even values of n. And the reason we couldn't do it for 19 is because the group did vanish for SL2 of this ring when D is 19. So our general strategy just didn't work in that case. So it's not, I don't know. I'm not sure I have a better conceptual reason than that. I do not even understand, um, on a moral level, why in the n equals 2 case you should have vanishing for 19 and not for these other ones.
I mean, but that's what makes it so interesting, right? There's this weird like mix of just special cases that just don't fit in.
Absolutely. Yeah. I absolutely think there's stuff going on here and I wish I understood it better. Thank you.
Thanks.
Um, Excellent. Okay, so let me say something about the big picture of how we can approach a program like this, which I also think is pretty cool. So let me just scroll all the way over. Okay. So, not very good at using this iPad. Okay, great. So here's the background to this entire program. The key fact is a result called virtual Beer-Yakman duality for the special linear groups. And so I'll explain what that is, and let me say a little bit of something about where that comes from. Very broadly speaking, I guess our approach to, the approach to studying these rational cohomology groups is to use the theory developed by Borel and Serre of the associated symmetric spaces. And so, right, so here's the story. What we do is we take our group and we embed it as a lattice, by which I mean a discrete subgroup with finite covolume, inside some product of copies of SLN of the real numbers and SLN of the complex numbers, okay? And in order to make it discrete, we're somehow going to use all the Galois conjugates of R to produce this embedding, okay? So this is the group I call G. And so then the key is what we want to do is use this embedding to study the action of SLNR on the associated what's called symmetric space, which is by definition the quotient of this G, this group G that we just defined, by a maximal compact subgroup. Okay. So great. So what are we doing? Big picture. What is group cohomology? Well, one answer to that question is group cohomology is the singular cohomology of a k-pi1 space for the group. At least in this case, we have for our discrete group. And so how do I get at that? Well, maybe what I want to do is if I can define a suitable group action of my group on a contractible space, then the quotient will be a k-pi1 and I can study its homology, its cohomology. Okay. And so unfortunately, in this case, we're not going to get everything we want in that sense. We are not quite going to be able to get a covering space action of our group on a contractible space, but we'll come close in the following sense. So, right, the first good news is that by general symmetric space theory, this symmetric space will be contractible. Okay. And we can do the warm-up case to have in mind is the case when n equals 2, where this space G is just SL2R, And the symmetric space X is the quotient of SL2R by SO2, the maximal compact subgroup. And actually this last fact is a bit of a red herring because it's a bit of a fluke of what happens when n equals 2. But in the case that n equals 2, we can identify the symmetric space with the hyperbolic plane. And we can do that by saying, well, if I have a matrix A, B, C, D, then we can map it to the point A plus BI over C plus DI. And you can check, I mean, just by, the orbit stabilizer theorem, that's going to give you this identification of SL2R sets. And it turns out this identification is also compatible with the hyperbolic metric on the hyperbolic plane. And so, in fact, this action by SL2Z corresponds to the usual action by Mobius transformations on the hyperbolic plane. Again, this is a bit of a fluke of n equals 2. We do not have the same hyperbolic space identifications in higher values of n. But right, in this case, we can see explicitly what's happening. So here's the famous picture of the upper half plane. And shaded in gray is a fundamental domain for the action of SL2Z. And so, right, roughly that means that the action is going to tile the plane by translates of this set, which you can see in the picture. Right, as advertised, it's going to be this fundamental domain is finite volume. The quotient will have finite volume. But I guess maybe the first point of disappointment is that the quotient is not going to be compact. So it has this fundamental domain has this cusp. Right. From the point of view of studying group cohomology, and especially from the point of view here, this program is about studying the high degree group cohomology. We would be really, really happy if we could find a K-pi1 that had the homotopy type of a compact manifold, because then we'd get Poincare duality. And unfortunately, that's not in the cards. It is not the case that the group SL2N of a number ring satisfies Poincare duality, but we'll see it satisfies something related, and that is what we're working towards right now. Okay, so in general, for general N, what do we get from this construction? Well, the symmetric space X is a smooth manifold. And good news is that the action of SL and R on X is properly discontinuous in the weaker sense of the term. So it's almost a covering space action. But the first piece of bad news is that this action is not free. It's almost free, but it has finite stabilizers. Okay, so right. So we have not quite a covering space action of SLNR on our symmetric space. And how can we fix this? Well, I guess one way is if you are happy with the theory of, say, stacks or, say, orbifolds, then maybe you're happy enough with the situation as it is. But even if not, something that you can sort of check directly just from first principles is that in a situation like this one, even though the quotient space is not a K-pi1 for our group, it will still have the same rational cohomology as the group and rational homology. So somehow finite stabilizers, somehow because rationally finite groups are their representation theory are always projective. it turns out that the finite stabilizers are not a problem from the point of view of rational cohomology. So the upshot is that the rational cohomology of SL and R is going to be isomorphic to the rational cohomology of this quotient. Okay. And so the next point is that unfortunately, the action is not co-compact, as in the quotient is not compact. And so again, it is not the case that SLNR has the homotopy type of or rather has the cohomology of a compact manifold. It is not a Poincare duality group. But there are various ways, including one defined by Borel and Serre, to compactify the quotient. Okay, so one way, this is not quite the Borel-Serre construction, but one way to think about doing this in the case of the plane is that we want to somehow add in some additional points, in this case, a discrete set of points, so that the quotient will be compact. So we want to add a point at infinity, and then more generally, we want to add a point at each rational real number and so topologically, this is a discrete set of points. And we've done this in such a way that the action, I mean, we can do this in such a way that the action of SL2Z extends over the new stuff that we've added in and that the quotient is compact. So more generally, Borel and Serre constructed what they call a bordification of the symmetric space. This is something that, I guess, from the point of view of smooth topology, it's what you would call a manifold with corners. So topologically, it's a manifold with boundary, but with some sort of distinguished stratification of the boundary. And this is done in such a way that the bordified space is still contractible, and that the action of SLNR extends over the new space. Okay. And crucially, now the quotient space is compact. Okay. And so in the Borel and Serre construction of this space, let me see here. Let me shift this over. So the new stuff that they added, which I will call informally the boundary, has the homotopy type to a simplicial complex that I'll call TNF. This is the Tietz building associated to our ring R. So let me define the Tietz building. The Tietz building, we're going to let F denote the field of fractions of R. So it's in other words, it's the number ring, or sorry, the number field associated to the number ring R. In the case of R, when the case that R is Z, then this is just the rational numbers. And then the associated Tietz building is, by definition, an n minus 2-dimensional simplicial complex. It's the complex where the vertices are non-zero proper subspaces of the vector space f to the n, and the p simplices correspond to flags. So that is to say, this Tietz building is the geometric realization of the poset of proper non-zero subspaces in this vector space Fn under inclusion. Okay. And there is an action of SLNR on this simplicial complex by simplicial transformations. Okay. And crucially, Solomon and Tietz proved that this building, this simplicial complex, is homotopy equivalent to a wedge of spheres of dimension n minus 2, infinitely many spheres of dimension n minus 2. Which means that it only has a single non-vanishing homology group. That's the homology in degree n minus 2. And this single non-vanishing homology group is called the Steinberg module. Okay. And this is the Steinberg module. Here we're viewing it as a representation of SLNR. So the upshot of all of this, the upshot of this whole story, if you combine the Solomon-Tietz building, the fact that this is a wedge of, the boundary is a wedge of spheres, plus just a formal application of Poincaré-Lepchat duality, what we can conclude from this is this result called Beery-Ekman virtual duality, which states that SLNR is, well, not quite a Poincaré duality group, but it does satisfy this twisted form of Poincaré duality, which says that I can identify the codimension I cohomology of the group with the dimension I homology, except at the expense of taking twisted coefficients and taking twisted coefficients in this representation that is the Steinberg module. So, okay, so great news. We've somehow reduced the problem of studying really high degree cohomology to studying low degree homology. Except now, to do so, we're going to have to understand the homology of this Tietz building. And in the statement here, this is, oh, actually, sorry. The Steinberg module is called the dualizing module. Okay. So, okay. So going back again, what is group homology, group cohomology? Well, okay, on one hand, group homology is the homology of a k-pi1. On the other hand, group homology, you can define it as a certain Tor group. And significantly, to compute a Tor group, we can resolve either of the coefficients. And so a formal consequence of that is that one of the ways that we can compute the cohomology of these, or rather the homology of the special linear group with these twisted coefficients is the following procedure. We can take a resolution of the the resolution of our coefficients of this rationalized Steinberg module by flat SLNR representations. We can take SLNR coinvariance, in other words, we mod out by the action of the group SLNR, the result of the chain complex, and then we take homology of that chain complex. Okay, and that homology is the homology, or equivalently these cohomology groups that we want to compute. And so the entire program that we're pursuing now, one approach is now to adopt the goal of trying to compute nice resolutions of this Steinberg module. And whereby nice resolution, I mean, on one hand, it better be a flat resolution, but really what I mean is it needs to somehow be a small enough resolution that we have some hope of being able to compute the coinvariance. We have to be able to understand what happens when we mod out by the action of SLNR. Okay. So, great. Good news is that, what's the first step in computing a resolution? Well, we want nice generators. And there is a beautiful picture that whenever I have an ordered basis of my vector space Fn, then I'm going to get an associated oriented simplicial sphere in the Tietz building, which is called an apartment. It's going to be a copy of the corresponding Coxeter complex. But in this case, in the case of SLNR, this is something we can understand extremely concretely. So if I take a basis and I just take all subspaces generated by non-zero proper subspaces of that basis, then it's not too hard to check that what we get is going to be the barycentric subdivision of the boundary of an n-1 simplex. Okay, so we can understand these spheres really explicitly. Here's the picture when n equals 3 of one of these apartments. And so the image of the fundamental class of these apartments is called an apartment class, the homology class in the Steinberg module. And Solomon and Tietz proved that the Steinberg module is generated by apartment classes. It's not freely generated. It's not even a basis as an abelian group.
Jenny,
But
could you scroll to the left? Because I think
oh, I'm sorry.
ours is slightly cut off from.
Sorry. Yes,
Thanks.
thank you. Great. So the Steinberg module is generated by these apartment classes. And so, okay, so one of the goals of this program is to somehow, first of all, refine this generating set to come up with smaller generating sets where it's easier to understand the action of SLNR. And more generally, we want to build not just generators, but also relations and higher syzygies for the Steinberg module. So somehow one of the approaches that was kind of initiated in the work of Church and Putman, is to do this using combinatorial simplicial topology, that somehow we want to build nice simplicial complexes that are somehow built out of bases for, let's say, z to the n, in the case of r equals z, and then somehow add more cells to these complexes to make them higher and higher and higher connected. And on the other hand, study maps from these complexes to the Tietz buildings so that, somehow we can use some certain relative homology, simplicial homology groups to construct our resolution out of chains on these combinatorial simplicial complexes. And in this work, somehow the hardest part in the proofs typically is proving that these bigger and bigger and bigger complexes that we're building are highly connected. So the hard part is showing that the homotopy groups vanish in a range, which is what we need in order to prove that the resolution we're building is exact. So, right. So somehow there's a lot of like dirty hands-on simplicial combinatorics that goes into the proof. And oh, I'm sorry, I'm already 2 minutes over time. So I'm going to maybe just like speed talk through the last two slides. Unfortunately, I did not get a chance to talk about connections to algebraic K-theory very much. I apologize. But good news is I realized that Jeremy Miller actually spoke in this seminar a few weeks ago. And so hopefully he was able to talk about the Rogness conjecture. I don't know if he mentioned the connection between that particular conjecture and the Farb Putman results, but it's a fact that a resolution of the Rogness conjecture would imply the Farb Putman conjecture on the vanishing of cohomology for SLNZ. So I think that's certainly very interesting. Conversely, it's a fact that if we could prove the Farb Putman conjectures, then combining that with known computer results, we at least think that we could then apply the method, of Alexander Kupers and co-authors, the methods they use to prove that K8 of the integers vanishes, to prove that K12 of the integers vanishes. So if you're motivated by algebraic K-theory, then you should help me prove these conjectures. On the other hand, let me I'll just in 1 minute. There has been more recent work by Ash, Patzt, and Miller, and independently by Brown, Payne, Brown, Chan, Gladius, and Payne, showing that a certain product structure you get on the Steinberg modules extends to give you some sort of free graded commutative algebra structure on the direct sum of all of the copies of the general linear groups GLNZ with coefficients in the Steinberg module. And I think this is pretty exciting for several reasons, one of which is that it gives you lots and lots and lots and lots and lots of new unstable cohomology classes. And I wanted to, at the very end, give a pitch. There's continuing work in this direction on trying to prove the analogous statement for the symplectic groups. The analogous statement is actually not that analogous. It turns out to be different and interesting. But at any rate, that is work being done by Miller, Patzt, and Peterson, and my PhD student, Urshita Pal. So I'm very excited to see what comes of that work. Okay, thank you very much.